Okay, good. Thanks a lot. So welcome everyone to the next Sydney CPPC seminar. And today's speaker is Martin Sevior from the University of Melbourne. Martin is an experimental particle physicist working on Bell, Bell 2, and Atlas. And he did lots of contributions to on the computational side and the analysis side. But today he will be telling us about something completely different, looking at particle and nuclear physics at the MeV scale, and basically to design a new experiment to test the ATOMKI anomaly and also to look more generally at the MeV scale. So please, Martin.
Well, thank you very much, Michael, and thank you very much for the opportunity to talk about this. So this is something that we've been interested in for quite a while. Ever since the second ATOMKI anomaly came out, which was the result on helium, on tritium. So this is now a relatively large collaboration between Melbourne, ANU, Adelaide, and INFN. And yeah, we have a number of master's students, postdocs, who aren't actually employed yet to work directly on this, but they've found time to contribute, and full-on professors. So let me get into it. Okay. All right. So, to cut a long story short, this is the short story. So theoretical studies in experimental anomalies motivate a high-precision time projection chamber for the Pelotron, which is a 5 MeV accelerator at UniMel. So I actually did my PhD on this accelerator. It's a marvelous device, and it's been doing great physics for well over close to 50 years now. Maybe David can tell me exactly when it started, but maybe we should have a little celebration soon. So this thing also enables qualitatively new types of nuclear physics experiments that are not possible, and it employs advanced detector technology developed for high-. And the key for all of this is high-resolution studies of electron-positron pairs initiated from proton-induced nuclear reactions, where we have an E plus E minus in the final state. And to start, and what I'm going to almost entirely focus on today is proton-induced reactions on lithium-7, which makes beryllium-8, and at around 18 MeV, which subsequently decays to an E plus E minus pair. And then a very recent thing is that we've initiated micromegas detector development in Australia. I'll talk a little bit about that and how that's going. All right. Start off with the motivation for doing all of this, and finish with, we'll start with the particle physics, the theoretical motivation for it. So as we all know, dark matter encompasses basically a whole collection of, or solves a whole collection of gravitational anomalies. And if you do all the large-scale calculations, including early universe calculations, you find out that dark matter makes up around 80% of the gravitationally effective matter in the universe. Now, if you run this back through the Big Bang baryosynthesis, nucleosynthesis process, then in order to get the right numbers of the light elements, then you need MeV-GeV thermal relic dark matter, and which requires, if you're in the MEV region for your dark matter particle, then it requires a new comparatively light mediator to achieve the required annihilation cross-section for thermal freeze-out. So if you don't get this, then nucleosynthesis in the early universe doesn't work, and you get the wrong abundances for the very light elements, like lithium. So basically, this goes all the way back to Leon Weinberg in 77. And so if your dark matter is less GeV, you actually need some new mediator in order to make all of this work. So because this cross-section is too small. So you need a dark matter particle, the chi. Yeah, well, just call it chi. and a new mediator, A prime. So this is the dark photon, which can mix with the standard model photon, and this generates a coupling to standard model fermions by their electric charge. So basically, if you have some sort of dark matter interaction, then this is mediated by this dark photon. This dark photon can mix with a regular photon, which can then couple to a regular E plus E minus pair. So this coupling is weak, well, feeble. We'll call it feeble rather than weak, because weak has a specific particle physicist. Feebly coupling, and basically to look for it, you need a very large source of photons. So you can actually make a lot of photons in nuclear reactions at around, and if you fire protons at lithium at around 18, with around 1 MeV proton energy, you populate beryllium-8 at 18 MeV, which can decay by and then this photon can potentially mix to a dark photon and make an E plus E minus pair. And just to put it in perspective, we can actually produce a lot of these on the Pelletron. So around 2 by 10 to the 11 over a thermo. So this is actually interesting sensitivity. All right. So another motivation, axion-like particles helps. So the QCD Lagrangian has a CP violating angle similar to the CK. So it's basically just a parameter out the front here. And this parameter is an angle in the range of 0 to pi. So in the CKM matrix, these angles are actually, of the order of 0 to pi, well above 0. But the neutron dipole moment implies that this theta is actually really, really tiny, less than 10 to the minus 10. So it begs the question, is it into this tiny, tiny little piece of parameter space, and the parameter space which encompasses 0. So this is what's called the strong CP problem, and it's solved with a new symmetry, a new singlet scalar field called sigma. The scale of this field is very, very much larger than 1 TeV. It's given by this factor F. And then this field acts as a space-time dependent field to cancel this theta, and it gives rise to pseudo Nambu-Goldstone bosons, the axions. So in order to make this theta precisely 0, we need a new field, and this new field has almost 0 mass bosons, but not exactly. So this is a Nambu-Goldstone boson, spin 0 minus, feebly couples, but once again, it's a different feeble to the dark coupling, but as opposed to weak, it feebly couples to gluons, photons, and fermions, and with different coupling strengths for each. Okay, so let's go on to ALPs. So axion-like particles arise from an additional global symmetry in addition to this axion field, if you like. So it can arise from global lepton number symmetry, global family symmetry, quantum gravity. Any one of these additional symmetries basically alters how this axion field couples. And then our standard model Lagrangian has components that couple to the gluons, to the fermions, and the fermions there, and to the photons. All right. Then the particle coupling to this, corresponding to this excitation, is the axion, and then excitation to the axion-like particles. And then in principle, ALPs can have different couplings to gluons, photons, and fermions. And nuclear decays, which are sensitive to gluons, can explore a viable ALP parameter space and hence is sensitive to multi-TeV physics. So this is kind of cool and exciting that we can do the experiments in our little Pelletron and start probing multi-TeV physics. All right. So this whole ALP regime is great fun for experimentalists and theorists because there's all sorts of different ways you can go. Andrea gave me this very, very nice slide showing all the places you can go looking for them. So we're looking around here with around about a few MeV worth of mass and a weak coupling. This shows the coupling to photons, but we're looking at the coupling to gluons. All right, so that's the theory background about why it would be interesting to look at do particle physics experiments with the pelletron. So here's some experimental reasons for why it's particularly interesting. So we have well-motivated theories for the existence of these feebly interacting fundamental bosons at the MeV scale. The ATOMKI group have found evidence for something like this at 17 MeV invariant mass, called the X17. This is sort of what their apparatus looks like. They fire their proton beam down into the middle of this thing here, and then they have a collection of sodium iodide detectors and position-sensitive detectors around that, and they measure the electron-positron pairs that are emitted via nuclear reactions. So, sorry, these are plastic scintillators, not sodium iodides. All right. So go back a page. So they initially found this running on lithium-7. Lithium-7, beryllium-8, and they found an anomaly in the angular distributions of the plus E minus pair. They repeated the experiment on tritium and found the same anomaly, but actually kind of a stronger signal for it back in 2021. And this is when I got interested. And this is when we started talking with Tibor and Andrew. And then just last year, they did another experiment on boron 11, and they found the same anomaly with approximately the same strength, all at around about the same mass. So the initial signature was an unexpected larger yield of E plus E minus events at large opening angles. A much better signature would actually be to measure the invariant mass of the E plus E minus pair. So that would tell you exactly what the mass of this particle is, and it has sufficient resolution, you can measure what the mass is. An opportunity to do fundamental physics research on the pelletron. And so we all got very interested in this. All right, so just put it to show you the data. This is the initial observation, proton on lithium-7 to make E plus E minus. And this is what it looks like. So here is, so we're going from A, B, C, D. So I'll actually go one at 0.8 MeV. And this is the angular opening angles of the E plus AC. They increase it to the energy to 1.04 MeV, and they start to see an excess. They run at 1.1 MeV, and the excess increases. And then they run at 1.2 MeV, and the excess goes. So this sort of all by itself looks pretty interesting. All right, so we have this excess at large opening angles on lithium. So they did the same experiment with a different setup on tritium. So this is actually challenging, making a target, keeping it cold enough so that the tritium didn't. So they had a very, very cryogenically cooled system to keep everything frozen in place. And I shudder to think of all the safety hoops we'd have to jump through to run this on the pelletron. So I'll leave this for the time being. But nevertheless, they found an excess of energy at large opening angles at all the energies. And this is because if the X17 exists, when you run on tritium, you're well above production rate for the X17. You're basically doing this in free space. You're not going through a resonance. So here you're actually hitting a resonance in beryllium-8 at 1.05 MeV. Here the boson on proton making making gamma rays or making whatever it is that is creating this anomaly. So there it is in tritium. And then here it is in boron. So they ran at 1.5, 1.7, 1.8, and 2.1. And sort of going back, well, going up from 1.5 MeV, okay, not much of a from expectations. Run at 1.7, and suddenly you see something. It's about the same again. 2.1, it's beginning to decrease. All right, so 3 different experiments, 3 different anomalies, and all of these, if you naively just look at the difference between what they claim is their background and what they claim is and their data. So of course the big issue is whether or not there's some additional backgrounds here. It's big, like it's of the order of 7 or 8 sigma. So, if the LHC found 7 or 8 sigma effects in 3 different experiments, there'd be no one would be jumping up and down, and theorists all over the world would be scratching their heads and trying to invent new theories to explain this. But, it's not that there's been no attention to this, but it's nothing like the sort of that you would expect if this was sort of at the LHC. So it's basically because no one expects it. And, essentially, it's not a popular thing to do. Nevertheless, I'm honest here and say no one else has looked with this level of precision that these people have. There's been no previous experiment. There have been previous experiments that have looked for E plus E minus pairs by nuclear reaction, but they have anything like. These guys have an order of magnitude more sensitivity than previous experiments. So it's not a priori unreasonable that they might find something. And as I said, there is some, viable, well-motivated theory that says actually there could be something here. All right, so in a nutshell, new physics might exist at the MeV scale, and it's observable via the X to E plus E minus final state using the Melbourne pelletron. So what we plan to do is build a far better experiment than what the group did, and perform far higher precision experiments with the pelletron. So just to put it in perspective, basically he measured the energy of their E plus E minus pairs using scintillation counters. So they basically just absorb them in scintillators. And so the energy resolution that they get is around 1.5 MeV. Furthermore, they can't track the plus E minus pairs back to the source. So you always wonder, well, maybe there's some other background that's making the scintillation light and firing the position-sensitive detectors as well. On the other hand, I'll tell you how we managed to achieve this. The TPC energy sum resolution is 0.1 MeV, so over an order of magnitude better. And then we can put nice tight cuts on this and discriminate against background. And then furthermore, because it's a tracking detector, we can determine the opening angle of the E plus E minus pairs very well. And so you go from the invariant mass resolution that ATOMKI got, here it is here, this curve. This is the invariant mass resolution, peaking at around about 17 MeV, to what we would get with our TPC, and basically we get around 0.1 MeV energy resolution, so about a factor of 20 better. So this buys us a whole lot more sensitivity. And so if we produce spectra like this, I'm sure that many would be very interested in our result. So particle physics, when we build this, will enable a whole collection of new types of applications. So, for example, we can make the world's first double differential internal pair production cross-section measurements. So basically, IPC is a difficult process to measure both the energy and the momentum of both the E plus and the E minus over a large opening angle. But we can do that with this time projection chamber. Trigger with one scintillator instead of two. Although, all of ours, this analysis that I'll describe today uses two scintillator triggers. So because we have a large acceptance, it also enables investigation of multi-particle final state. So for example, we could look for unobserved two quantum nuclear processes, which have been observed for gamma decays, basically all gamma which was first observed back in 2015, which for double internal pair conversion using the time projection chamber. So both of these kinds of investigations are qualitatively new sorts of investigations for nuclear physics. So for example, this first one we can use to determine spins and parities for states where these are unknown. And then this is kind of a new kind of quantum effect that we can use our nuclear target as an interesting quantum laboratory to investigate. All right, so this is the time projection chamber, which we hope to build and install on the Pelotron. It's not very big. So the internal diameter of this thing here is just over 30 centimeters. It's 16 centimeters from the center of the beam to the edge of the scintillator. So the whole thing's just a bit over a foot across. All right, so we fire our proton beam down a tube through the middle of this, and we put a target in the middle of the whole detector. So if you look at this proton beam down here, put a target there, and then we initiate our reactions on this. All right, so to make a time projection chamber, you need a very uniform. We build this with a collection of electrodes arranged as concentric rings to basically define a very uniform electric field. So this is called an electric field cage. All right, so go on to the next slide about this. So this is sort of the easiest way. So this is a time projection chamber side view. So you have a magnetic field generated by our electromagnet, a nice uniform electric field, magnetic field, and field as well. So the electric field is designed to be uniform. It's defined by this collection of rings around the inner and the outer side. And basically, we start with around 15,000 volts and we step it down in a uniform way, a whole collection of resistors down to 0 volts down here. At the end, we have a micromegas wire mesh. So this is just a wire mesh. It's basically a stainless steel wire mesh that you might use for very high precision filtration. So this gap between the wires is of the order of 15 microns. So very, very fine wire mesh. So this is held at volts, and then we apply an 800 volt potential between this wire mesh and a collection of strips on top of a printed circuit board. So this wire mesh is only around 100 microns above this 800 volts. So this makes a very high electric field region. So what happens is our ionization electron, which, all right, let's start off again. Target plus and minus pair goes curling through the magnetic field, which we don't see because we're looking side on here. And as it goes through a noble gas mixture, it ionizes the gas and liberates electrons. So these electrons are liberated because they're in an electric field, nice uniform electric field. They just drift with constant velocity to this wire mesh. They find their way through the wire mesh to this 800 volts. And when they enter this region, they undergo gas amplification. Because if you have a very large electric field, you get a of the order of a 10 to the 4 amplification in the number of electrons. So you start with one electron, you end up with around 10 to the 4 at the end. This produces an electromagnetic pulse, and this electromagnetic pulse is then picked up on a collection of strips buried in a printed circuit board. So we have strips below in the X direction and the Y direction, and then we can localize where this happens by the pulse distribution on these strips. Upshot of all of this is that we find out the location in X and Y very precisely of all of these, of this ionization. And then we can use the time it takes for the electrons to trigger the time projection chamber at the end, and the time it takes for the scintillation counter to fire to map backwards, because these electrons drift with you. So because of this, we can work out the Z direction as well as the XY direction of where this electron came from, and hence we get XY and Z position of the particle track. All right, so that's the principle of a time projection chamber. Okay, so talk about the design of the TPC. So the conceptual design was made using the Eve package and route. Really clear. I'm very pleased that I did this, and I'll explain. You'll see why this was such a good idea. We'll simulate the electric fields inside the TPC and Micromegas with the Conceptual multi-physics package, and David Jamison for giving us access to that. Gas-based detectors with high-energy called GAR. Simulate the passage of the primary electrons through the TPC with G-on-4. Record the space point hits with the expected resolution. Then we employ GenFit2, which developed tracking particle trajectories. Then we employ Xray to reconstruct the interaction point. So this actually does the vertexing. Then we employ Eve again to do the event display and visually validate the reconstruction, and I've got some nice videos of those. And then finally, we employ RootFit to determine the signal and the pressure. All right, so that's it in a nutshell. So first thing we need to do is build our electric field cage. So this is what it looks like in dimensions, and this is what it looks like in 2 dimensions. So we basically took out the rotational axis, and we just using the geometry with symmetry employed in COMSOL. All right, so you see these broken lines up and down here. These are basically these rings that define the electric field. Okay, so we step 10,000 volts down to 0 in uniform steps along the way. All right, so we tried a number of simulations of this, and we started off with, something. 9mm rings placed 1 millimeter apart, and we found a kind of it was sort of approximately uniform, but, perhaps the non-uniformity was about part in 10. But this was worked on substantially by a very talented master student, Nicholas Jackson, who's unfortunately left physics, but nevertheless, he optimized this, found a good collection of rings, 4.5 millimeter rings placed 0.5 millimeters apart, with the initial upstream ring 1 millimeter downstream of the cathode disk. And this makes a really nice uniform electric field over most of the TPC. All right, so next thing we did was simulate the release of electrons into this electric field. So basically, we fire our high energy electron along here, and we track how probable the electrons, how probable it is that electrons are released. And basically, we found around 100 electrons per track are released by ionization, and then these are propagated down towards our detector. All right, so what we did then was we found that there was some residual correlation between the initial radial position and the final location in the XY regime. So this is our initial predicted error. It's around about with a precision of around 100 microns. But then when we make this correction, we get resolutions that are much better, of the order of 10 microns. So using this process, we can basically take the non-uniformity of the electric field into account, and we're basically left with getting our XY resolution around the precision of the micromegas detector. We also did simulation velocity, and we basically have around about a 1% precision. So the electrons don't drift with exactly the same velocity all the time. There's a mean and a sigma of around about 0.0 centimeters per microsecond, and this gives rise to a Z resolution of around. So we'll see the effect of that in a minute. All right, so next, the COMSOL and Garfield simulation of the micromegas. So these lines here are basically the drift lines of the electrons. So we did a simulation of this, and we found that over 99% of the electrons find their way through this wire mesh. They're basically repelled by the 0 volts, or basically the field lines map their way around these the mesh held at 0 volts and are attracted to the plus 800 volts on the other side. So electrons manage to drift past all of these lines and find their way onto the action region. All right. So once there, we made a simulation of the micromegas. So this is sort of a visualization of what happens with the. We did simulations over a range of voltages applied to the strips, and we found when we run at 800 volts, we get over 10 to the 4 gas amplification, which is great. And then this induces pulses of around 5 picocoulombs on the readout strips. So this is the readout strip position in the X direction and the Y direction. And what we can do is do a center of gravity of the size of the pulse across these strips and basically interpolate between those to determine where the electron actually. All right. So what we have to do is actually read these things out. So we can actually employ LHC electronics for this. So these VMM ASICs and scalable readout system were developed for the, I think it was Atlas and CMS upgrades. Basically, the VMMs were developed for micromegas detectors for what are called the Atlas small wheel units of the tracking volume of the Atlas detector. Beautiful things. So basically, picocoulomb pulses from the strips are in the right range for a VMM linear response. And furthermore, this has a very nice long digital pipeline. So basically, it records the channel number, the analog charge, and the time with 1 nanosecond resolution and a 64 microsecond dynamic range, which is fantastic because it takes around 30 microseconds for all the electrons to drift out of our TPC. So we can capture all of this information in the VMM ASICs and scalable readout system. So that's our plan there. All right, so putting this all together, this is our projected XY resolution. It's of the order of 100 microns. So basically we do this gravity between the pulses, and we end up with around 100 micron spatial resolution. All right, so that's what we feed into our Xeon 4 simulations. So as charged particles propagate through matter, they interact. Basically, they do multiple small angle scattering, which causes a direction change. So every time they change direction, you lose a little bit of information about the initial trajectory, which is not a good thing, because what we want to do is know what the direction of the electron was as it was leaving its nucleus. And so the more multiple scattering events you have, the worse your resolution, the worse your invariant mass resolution will be. So we've set up a Xeon 4 simulation of the TPC to do this, and to make the best detector possible, we want an accurate determination of the invariant mass of the plus E minus pair, and that requires precise measurement of both the magnitude and the direction of the charged particles. So we need an accurate simulation of multiple scattering, and to minimize the effect of multiple scattering, you want low density and low Z material. So basically all of our noble gas is 90% helium and 10% CO2. So that's what we used in all of our simulations. Helium, mostly helium, to minimize multiple scattering and energy loss. All right, so we've got our particle trajectories, and what we need now is turn these into tracks to determine the momenta and to determine the opening angle where they basically left the nucleus. So we've developed Reconstruction software and fits HEP software library to reconstruct the tracks. So just to let you know, Bell 2 uses GenFit as well. So it's kind of nice to reuse a bit of Bell software for this purpose. And we developed Vertex Reconstruction software using the Xray HEP software library to project tracks back to a common vertex. And once again, this is employed by Bell. But I have to say this was a pain to make work because there's a bug, a C++ bug in it that took me ages to work out why it wasn't working with a modern version of C++, but it did work with an old version of C++. But eventually we got that fixed. So this is really useful because with the vertex reconstruction, we can basically apply additional constraints to our trajectories. So basically, we can apply the constraint that both trajectories have to come from the same point. And furthermore, we can require that they come from 0 at Z equals 0. So those extra constraints on the trajectories improve our invariant mass resolution. All right. So we made numerous simulations, including 100 micron resolution in X and Y and 1 millimeter in Z. We found detector gas, 90% helium, 10% CO2. And one final little wrinkle, a thin target chamber wall provide very good invariant mass resolution. So if we have a chamber wall, so we have around 1 millimeter thick, say carbon fiber, which is what ATOMKI used, then we have an invariant mass resolution of around 0.4 MeV. However, if we instead use a very thin chamber wall, 50 microns of mylar, 50 microns thick mylar, then our invariant mass resolution drops to 0.1 MeV. Okay, so this was exciting, but raised the question of whether or not this would actually work and not break when we pump out our chain. So our best invariant mass resolution requires a very thin vacuum wall, and the shear strength of mylar foil is 15 kilograms per millimeter squared, and this implies 50 micron thick foil has around a factor of 20 safety under vacuum. So you just do some back of the envelope, notebook size calculations. Puts 10 to the 5 newtons per meter squared pressure on this target chamber. So basically, this is where we would fire our proton beam down. We'd make gaps around where we'd place our target here, and we'd cover this gap with mylar, 50 micron thick mylar. So here it is here, and here it is under vacuum. We did this under construct. This is our target assembly under construction. So we just glued it in place with Torseal, and then we used these high-tech rubber bands and pieces of bamboo bought from Safeway to hold everything in place, let it all dry, unwrapped it, and then pumped it down, and we reached vacuum of around 5 by 10 to the minus 5 torr, which is basically limited by the outgassing in this crazy little system we use to attach our tube to a vacuum pump. So that was great. That all worked. All right, so now let's talk about background. So there's two main sources of background. The most important is internal pair conversion. So this is IPC. This irreducible background comes from nuclear internal conversion, where you start off with an excited state of beryllium. It decays via a gamma, and then while this gamma is still inside the nucleus, it interacts with the nuclear field, the electric field in the nucleus, and this pair. So because this arises from a virtual photon, it peaks at low invariant mass. So basically, this was simulated using the Born approximation, the software provided from our ANU collaborators, particularly Tibor. So we did a full G-on-4 simulation, reconstructed everything with GenFit and Rave, and we used realistic hits, and this is what the distribution looks like. So, peaks at low invariant mass and extends all the way out to 17 MeV. So the name of the game then is to make our invariant mass resolution as small as possible to distinguish our signal above this irreducible background. So if you remember the Higgs to gamma search, basically the only way they could find that under the massive background of gamma pairs is because they had sufficient mass resolution. All right, so another background is external gamma conversion. So this is where we actually have real gammas that make it out of the target, and then they interact with some material and make an E plus E minus pair. So once again, this is peaked at invariant mass. We simulated around 10 to the 8 of these, but because we have a very low mass near the target, this limits the conversion to less than 0.1%. And then because we're applying Rave, this vertex constraint, basically saying, this E plus E minus pair has to come from the target, that really cuts down this background. So this is our background with the cuts. There's almost nothing out at 17 MeV. So our background, this background is negligible compared to IPC. All right, so I guess I'll skip this, but basically we can collect data fast enough. That's not a problem. All right, so I thought I'd show you some videos of this thing in action. So this is the signal E plus E minus simulation. So here's our target in the middle. So you can see the E plus E minus pairs coming out. Of course, everyone knows that positrons are red, electrons are blue. So there they are there. The fun thing about doing everything in Eve is that you can make these simulations really nicely, and you can make event displays really nicely. All right, notice the big scatter in Z. Okay, so we have 1 millimeter resolution in Z. That doesn't really affect things very much. So when we look side on, that Z information is here, and you can just see a very good XY resolution. You can see that we can track our particles back to the interaction point. However, all of these signal events have these very large opening angles. Okay, there's big, large opening angles from the signal X17 events. This vertex of putting the interaction point exactly where the target is provides extra information that we can use to determine the invariant mass of the E plus E minus pair. All right, so this is some videos of our background. You see, So you can see the opening angles for all of these are much closer together, all right, because literally they're starting from virtual photons, which have 0 MeV invariant mass. So basically our electron-positron pair wants to have a small opening angle. So this video is not working all that well. Anyway, still apply the vertex constraints and see all these events coming out with small opening angles. All right, so we use both the opening angles and the momentum measurements to determine that we have our X17, or if the X17 exists. Okay, moving on. So we did a full simulation and reconstruction of IPC and X17 with our 50 micron molar vacuum wall, and a 4-day run on the Pelletron. Do all the numbers. We find in 4 days we would find around 2,300 plus or minus 50 events. So this is what it would look like if we made a linear plot. This is what it would look like if we made a log plot, and we'd have 50 significance. So this would stand out like an absolute sore thumb if the X17 exists at the rate that ATOMKI says it does. All right, so that's only a 4-day run. We've got plenty of time on the Pelletron. What can we do if we make a 30-day run? So what we can do then is search for the X17 and then perform a bump hunt and set upper limits for other interesting things that might exist. So, a 30-day run, if the X17 exists, no problem whatsoever, 100 sigma significance. If instead an X exists at 200 times less than the ATOMKI rate, then we would still find it. Okay, we would still find this little blip here. And then what we can do is look at this distribution and estimate what's the probability that this background will fluctuate up to make a signal. And we can set a 90% upper limit for that. So this is what this 90% upper limit looks like. Here we are around 17 MeV, orders of below where ATOMKI says it would be. All right, so at 1.05 MeV, when this populates a spin 1+ state in beryllium, and so we can use that to set limits on the existence of ALPs. So basically what we're looking at is the coupling of ALPs to quarks and the coupling of ALPs to gluons. And you can see that our TPC can set the world's best limit on coupling of ALPs to gluons, although not quite as good of coupling of ALPs to quarks. But still, we improve the constraint on ALPs this way without. And so we also completely exclude the parameter space as viable from the ATOMKI experiment. So suppose we don't find anything at 1.05 MeV. Okay, what we can do is increase our energy up to 4.5 MeV. And then the good thing about that is the protons lose less energy when you run at higher energies. So you can make your target 10 times thicker. And then a 30-day run makes this 2 × 10⁻11 photons. And this makes a really interesting search for dark photons. So, for example, the world's best limit on dark photon production in this mass regime was made by Na48, who used Darlot's decays of pi zeros. And they only had 10 to the 9 pi zeros. So we have 2 orders of magnitude more photons. Furthermore, we can do a bump hunt in the invariant mass spectrum, and our exclusion, and we make the world's best exclusion for prompt weakly coupled bosons in the 5 to 22 MeV mass range. And this enables us to set world best limits on dark photons. So just to put it in perspective, this is the Na48 experiment. It's basically a high precision K-long decay experiment. But in the meantime, they they have a large production of pi zeros. They look at Darlot's decays of those, and this is the upper limit they set for Darlot's decays to some E plus E minus pair anomaly. So in this regime, this is where we're looking. This is where their background is highest. Okay, so they have a high background here, but we actually have a low background. So we can actually beat this limit quite handily. And so consequently, this is our exclusion for the time projection chamber from our 4.5 MeV run, 30-day run. All right, but that's not all. We can look at nuclear reactions as well, which have different Q values and it's endpoints. And so we can adjust the endpoint to look at different mass ranges and basically get our IPC background down below where we can actually search for interesting physics. All right, so I don't have a lot of time. People could ask me about competition later, but there is competition. And then finally, looking at these micromegas detectors, we realized that actually the technology for this is quite accessible. It's all PCBs and lithographic materials. So we can use these to make Xray detectors, and we've initiated a collaboration to do that very thoughtfully and what's the word for it? Recently funded by the Labie Foundation, initially to make a advanced undergraduate lab that makes a position-sensitive Xray detector. So, yes, out of time, so I won't talk any more about this. So, proposed CPC facility could exclude the X17 with greater than 2 orders of magnitude in an identical nuclear system. The full experimental and theoretical details are available on the archive. So we've made a publication, put it on the archive. We're just tidying up and putting some extra details in, and then we'll submit that to a journal. So this is a unique facility, provides a world-leading probe for dark photon out and ALP searches, significant first measurements for fundamental new physics, opportunities for interesting nuclear physics with a large acceptance IPC detector. And we've initiated a technology transfer for Micromegas detector development. And we have a proposal for funding in 2024, both a discovery project and a LEAF. All right, that's it from me.
Yeah. Thank you very much, Martin, for a very interesting talk. So we have time for questions. Maybe just to start us off. So at one point you mentioned that for the gas which you use in the TPC, you have that 90% helium and then 10% CO2.
Yep.
Why do you need CO2, or why?
Right. So it's CO2 because in the amplification region, you get a lot of ultraviolet photons. Mm-hmm. And if these ultraviolet photons can also liberate electrons elsewhere, you need the CO2 to absorb those ultraviolet photons and to limit the possibility for getting sparks.
Okay, good. That makes sense. That makes sense, because otherwise I thought helium would have been, well, lighter and yeah.
Yeah, unfortunately it's transparent to these UV photons.
Mm-hmm. Okay, thanks. Are other questions? Wait, there, hands up. Sorry, I didn't see. Bruce, let me go first.
Martin, thanks for the talk. All sorts of questions. When you were discussing the previous results from ATOMKI and so on, there was a comment about the reactions on tritium to produce helium-4.
Yep.
And why that was not a resonant reaction, but was instead continuum.
Yeah.
There's something I'm not understanding, because helium-4 does indeed have excited states in the 20 MeV region. I understand they're broad, but they're still excited states. So what am I missing here?
You're probably not missing much. You're probably observing my nuclear physics knowledge, Bruce. So basically, my understanding is that those states are so broad and overlap so much that it's almost like a direct capture reaction. And just from my reading of the papers, that's how people are considering the reaction on tritium.
Okay, so that there are enough of them that whatever energy you get something, whereas with the others, you're getting a specific resonance.
Exactly. So the beryllium in particular definitely populates a 1+ state. I haven't looked closely at the boron reaction to see what state it's populating in carbon-12. But that would be...
Okay.
Yeah.
Can I just ask one other question, then I'll give over to others. You mentioned earlier, and then at the start, and then you showed some limits later, that you're looking at nuclear decays that are sensitive to gluons. Is it my imagination, or is understanding the reaction of something with gluons at MeV energies something like everyone's worst nightmare?
I imagine it's someone's like everyone's worst nightmare, but I give over to my colleague Andrea Tham, who has worked out approximations for how you can do this. And I encourage you to read her papers to see how she manages to make sufficient approximations to get, intricate nuclear physics to the coupling of ALPs to gluons.
Okay. Right, thank you.
Thanks. There's another question by Yuki.
Hello. Thanks for the great presentation and very interesting talk. I have a couple of questions. So first one is page number 11. Oh, this one. Yeah. I was wondering for this middle plot with hydrogen target, why the opening angle is limited in the larger side. Do you know the reason?
So basically, I don't know the exact reason, but it's probably because their large opening angle requires detectors from behind. And for this experiment, they actually had to run a cold finger and stick their target on the end of this cold finger. So my guess is that the reason they limited that opening angle was because the cold finger got in the way of the electron-positron pairs.
So it's purely some geometrical limitation.
Yeah, I think so.
Okay, yeah, thanks a lot. And another question is in page number 16, you mentioned that you use Garfield. I know that there's a different version of Garfield nowadays, like using C++ or Fortran. Which one? Do you know which one?
Yeah, we're using the latest. Oh, we're using Garfield from 2021 C++ version.
Okay, I see. And so in your gas mixture in the simulation, did you include the diffusion effect? I know that it can be turned on or off.
Sorry, did I include what?
Diffusion.
Diffusion, yes, definitely.
And do you know how much diffusion you would expect from helium CO2 90 to 10?
Sorry, back up a step. When you say diffusion, do you mean the probability of helium to diffuse out of the detector? Or do you mean?
Oh, the diffusion effect is, when electron drift inside the field.
Oh, yeah, definitely.
They hit.
So you can see that in our simulations, that they're not straight.
Yeah. I see. I was wondering how much they diffuse with this kind of gas mixture.
It was just calculated with mag bolts.
Yeah. Yeah, thanks. And the last one is when you calculate the field map. Yeah. What's the potential of your beam pipe itself?
The beam pipe is okay. So I'll just go to here. So this line down here is where we're actually down here is where we actually have the field cage. So the beam pipe is held at 0 volts, and there's the outer surface of the TPC is actually aluminized kapton, which is also held at 0 volts. So if you look here, there's a really, really high electric field because it's like 15,000 volts.
I see.
And it's dropping all the way to 0 over meters. And this outer region here is just pure CO2. So, so we have pure CO2 outside this CO2 helium mixture to impurities in in our detector gas, but also because it's a very good insulator, electrical insulator.
Okay, I see. So the having the 0 volt in beam pipe doesn't affect the inside field.
Exactly.
Okay,
So,
okay.
so
I see. Yeah, thanks.
All right, so Mikhail had to run off. So does anyone else have any questions they'd like to ask Martin? So maybe I'll just take the last one. Do you know anything about the current status of like just the standard model explanations? Or I guess they'll be kind of complicated explanations, but these sort of strange QCD states like hexadiquarks and stuff like this. Do you know if these are considered reasonable explanations for this as opposed to like a new boson?
Oh, I haven't seen anyone talk about that at all. I mean, there are other beyond standard model models. As I said, the ALPs are viable, and I think there's a ring call on the dark photon models where you can have different couplings between the up and down quarks for the dark photons, which I think are also viable. But I haven't heard of that one.
I think people were trying to figure out if there was some like unusual higher order QCD state which could just be being produced in these things, but I don't know if they're sort of reasonable things or not at all. It's not something I've followed particularly closely, but yeah.
No, I haven't seen that. If you want to send me a link, I'd
be sure. Yeah, I'll send you the link to the paper that I saw anyway. All right. Anyone else? Final chance.
I have one comment.
Who is that? Oh, Giorgio.
Yes.
Oh, yeah.
Just to answer your question, I was seeing a paper a few days ago that was claiming to try to explain these effects with a higher order standard model corrections. So yeah, there could be maybe possible explanations, but I didn't have really the time to go through the paper.
So I saw a paper from a couple of years ago, or 3 or 4 years ago, where basically you needed to put the parameters describing internal pair conversion to unreal physical limits in order to get this effect.
Right.
But yeah, if there's an update on that, I haven't seen it yet. So yes, please send me the link.
And Bruce, do you have one final question?
Yeah, related to that, Martin, it was more a comment. You said that if LHC experiments had results at this statistical level, there would have been a like deafening fuss about it. I think the plots that you showed later in the talk essentially answered your own comment in that the fact that they're doing this with the equipment that they are, and they get a shapeless excess at high energy rather than the peak that you would get with the TPC.
Yeah,
I think that sort of explains it, because if you put a gun to people's head and say, can you absolutely rule out some mechanism that would produce an excess of high energy electrons or positrons from some nuclear reaction, then I don't know. I mean, that's kind of hard to rule out, whereas the peak would be definitive. I mean, it's sort of the point of your experimental proposal.
Absolutely, Bruce. You're entirely correct.
So
And you know, that 7-8 sigma thing is, you know, it was a bit flippant, and it was kind of a bit of motivation, but it's very naive. You know, people work really, really hard in these high energy physics experiments to work out what their backgrounds are, and they still get it. And so, you know, if you just have a small group, best will in the world, without, you know, experimental equipment, you can't be sure at all.
Yeah.
And so I get what you say about the gun to the head, you know, predict. And I agree. That's why we're doing the experiment.
indeed. No, and I understand this all a whole lot better now. So thank you very much.
Yeah.